So today I want to go over a interesting topic, at least interesting to me, which is simulating quantum algorithms. And up front, I'm not sure if most people know that you can actually do this. So let's define a few topics up front within this discussion. First of all, let's talk about what qubits are compared to bits. So a bit is a standard piece of information, right? It's a zero and one or one, and a bit is either a zero or a one, and that's pretty standard overall. What a qubit is a zero, a one, or zero and one. So it creates a third possibility, the zero and one. Think of it like with Schrodinger's cat, for example, right? Which is where this initial concept stems from in the real world with Schrodinger's cat, which is you put the cat in the box and then the cat is both alive and dead at the same time. So it's in that intermediate state. And then so what would that translate into in computer terms? And then what that translates to in computer terms is the qubit. And then the qubit is exactly that, a state of zero and one at the same time. When it comes to and actually enabling a qubit and getting a qubit to work, you need to enable it and have it work on quantum hardware. In order for it to work on quantum hardware, it has to meet a lot of real world conditions. Like it has to be super cold. Like, I mean, literally almost 0 degrees Kelvin, which is a lot less than 0 degrees Celsius or Fahrenheit, right? And then that's the main condition is it has to be super cold and can't be noisy. And then so within that, we want to simulate this environment. And then so we're going to talk about that and that simulation process here in a second. But so what exactly are we simulating within this? And then so what we want to simulate within this is quantum mechanics. And quantum mechanics are going back to that concept of the qubit of the Schrodinger's cat of zero and one or alive and dead, like this intermediate state. The quantum mechanics is the what is known and what comes out of the impacts of that. So we have concepts such as quantum entanglement, where two bits can be entangled together and can communicate across vast distances via quantum mechanics. And then we also have quantum tunneling, where a bit can cross a plane and cross a physical plane and then end up on the other side of the physical plane and somehow tunnel through that physical process via quantum mechanics. So there's a lot of quantum mechanics that we don't know how it works, right? We know that these things are emergent properties of this quantum process, of this fact that you can have 0, 1, or 0 and 1. And so we want to essentially just explore that further, right? So we want to explore this concept of 0 or 1 and 1 further and putting it into simple terms. And so that's exactly what we're doing in this instance. And then so how we are going to do that in this instance is we're going to create essentially we're going to call it a Nubit. And a Nubit is about a millionth as powerful as a qubit. And then so a qubit would be we're running quantum algorithms on quantum hardware. A Nubit is we're utilizing PSO swarm algorithms to simulate quantum hardware, quantum algorithms, and we're using Gaussian probability space to simulate our quantum hardware. So what does all of this mean in kind of more layman's terms overall? Kind of giving you more insight into this and my head around this. I'm very fortunate within my career, and that early on in my career, especially, I worked for kind of some big companies, Apple, HP, and Intel, very specifically, and then Intel a lot. And then so Intel during the time very specifically when dual core processing had just come out, and then so I had to deal a lot, and I had a lot of training with regards towards multi-threading and multi-core processing and what exactly that means, right? And then so with my knowledge of how exactly multi-threading and what multi-core processing means, to me, it's the perfect way to simulate what we want to do in this instance, which is quantum states. And then so let's say that my computer has 8 cores, just, for example, like 8, 16, 4, 7, who cares? Exactly. It's more than 3. All we need is 3, right? And then so in this instance, my computer has 8 cores, which we could, if we want to, we can break them down and they would function as 8 individual computers, which is what we want to do in this instance. And then so we want to take those individual cores, and then each one of the individual cores represents a fraction of a bit. So 0, 1, or 0 and 1. And then so we have the 3 different cores. And then in that instance, we play around with those cores, and then we play around within the Gaussian probability space. We play around with attention mechanisms and weights. And then so within our weights, attention is all you need. We put an attention mechanism onto everything, right? And then so kind of the first iteration that I have of this Nubit is what we're looking at here, this code that we're looking at here. And I wanted to essentially like iterate and see if this would actually work. So very first thing I do is I define a function that we want to optimize. So this is just a mathematical function, and then it's just simple mathematical equation here. And then we have our quantum exploration phase. So a lot of this is math, right? So then it's just essentially all of the math needed to get that 0, 1, and 0 and 1 states. That's what we're like simulating the probability of that. And then we have, in this instance, what I wanted to test out and see what happens is so if this is accurate, like if something happens within this, then we would see a difference by adjusting the weights in this instance, right? And then so in this instance, I've defined 3 weights: the global weight, the local weight, and the quantum weight. And then so how this works is that the higher the number is, the more that the model is going to preference that. So if global weight is 0.6 and local weight is 0.2, it's going to preference a global weight. It's going to preference the global weight 3 times more essentially than the local weight or the quantum weight, and then vice versa, right? And so that's kind of how that breaks down, and you can play around and adjust that. And then we have our subpopulations, and then our this is all of this is the math for the algorithms themselves. And then so essentially we're utilizing PSO swarm algorithms, and then each one of all of our swarm algorithms is going to later on is going to represent each particle will represent 1 qubit. But in this instance, we're just saying that we want to have our particles be represented by qubits, or do we want our particles to represent bits? And then here's a simple mathematical equation to do that. And then here's some weights for the attention mechanism. And then here's to go about that. And then here's the logic to use. So we want to do a number of states 10, number of particles 20, number of iterations 30, and subpopulations 3. So the reason why I brought up multi-threading and multi-processing to start off this conversation is that those subpopulations, as well as the particles, they're all utilizing multi-threading and multi-processing within this, right? So PSO swarm algorithms overall are a algorithm type that was invented in the early 1990s. And then I never have personally used them before multi-threading was a thing, but I can imagine that they would be a lot less useful on a multi-threaded computer. I don't know, because every single computer that now exists is multi-threaded, right? Which is something that we take for granted. But in the early 1990s, that was not a thing at all. And it wasn't a thing for 20 years later, which is why I think oftentimes a lot of people sleep on PSO algorithms, because they're one of the older algorithms, and because of the fact that 20 years of operating the same way, right? But I mean, essentially, like if you like, to me, just knowing what I know about multi-threading technology and multiprocessor technology and how swarm algorithms work, they go hand in hand, right? I don't understand. Like they wouldn't really work if you like on like a Pentium 4 or something like that. Like it would, this wouldn't be that good overall. Like this only works because computers are now multiprocessor computers, and then so. Why people don't explore this overall, I think that's the reason why, right? It's that mixture of these are older algorithms, and it was like 20 years before these were actually useful on any level. But as we can see here, they are useful, right? So this test number one, what I'm doing is testing to make sure and see that we can get some sort of difference, right? And then so we get some slight variation, which is what I was expecting and what I was wanting, right? So we can see that by adjusting the weights, we get some variation in our value, not in our values, not significant, and these values aren't very good. So we want this number to be as high as possible, and this number can go negative. So the next step is to start making adjustments to this, right? So that's what we start doing further and further in this code, is making more adjustments, adding more math, adding more functions, more like simulating more quantum functions for this to happen, right? And then so you can see we're still we're getting into negative values for our best position, and then for our best value, we're getting some improvements in some areas, but then worse in other areas. And you can see that we've made major adjustments to the weights here as well. And then so we go through, and then based off of all of this, we do more and more iterations. So still negative, but getting better. Going through, now we have two positives and only one negative, and this is barely negative, but our best values aren't that good. So we're getting into positive, but not extreme positive. So now we're focusing too much on avoiding negative, right? In this instance. So then we go through and we experiment more, and then we like kind of backtrack a little bit in this instance, and then we're like, okay, let's go back, and then same thing in this instance, we make progress again, right? And then so we go back up, and then we're just adding more and more. So in this instance, a little bit more progress in this instance. Like this is progress overall to me. This one, yeah. And then major progress here, right? So then we're iterating, and then we can start. We start seeing this is the major results of that iteration. We're starting to see like fruits of our value, fruits of our labor, and then even better results here, right? So we're getting like even better, and then. From here, we start playing around, and then we introduce some more essentially like quantum mechanics and quantum algorithms within this, and then we get even better functionality within this, right? And then so this is where I decide to create the Nubit itself. And then this is where I start to, okay, let's experiment with what a Nubit would be. So in this instance, we're going to initialize the Nubit state, and then we're going to initialize the state of each Nubit as a probabilistic representation, and each Nubit will have a simplified superposition state with discrete probabilities. So we're very specifically mapping out, again, either it's a 0, 1, or 0 in this instance is how we're getting the 0 and 1, right? And then so that's how we're simulating, just so you know. And then so in this instance, then we simulate all of the behavior, and then we've got our swarm algorithms. And then so in this instance, we run 100 Nubits, and then we run them for 30 iterations. And then so what's happening in this instance is we're taking our 100 Nubits and we're training them, right? And then so if the training is successful, we would expect this number to go up. We would want the position, the final best position, to go up. And so we can see after 30 iterations, it starts at 0.27, 0.278, and then ends at 0.289, which is pretty significant in these regards. And then same thing with the fitness, right? Starting a fitness of 0.908, and then pretty significant and pretty corollary, like that's what it is for the first two iterations, and then we end with a final fitness score of 0.909, so significant at 094, significant increase from 0.9080. So you can see that this is in fact like doing stuff, right? Which is exactly what we want to so why exactly are we going through this, right? Like, what is the point of all of this? What are all these numbers that we're looking at here, etc.? And then to me, that's the bottom line: is it doing stuff? And like when it comes to these philosophical questions around these models, like do they learn? Or can they utilize like quantum mechanics? Like can they like reason? Whatever the question is that you want to ask. To me, there's some sort of benchmarks that you need to be putting in place there, and then to me, it's important to realize that there's a difference between like small percentage and 0%, right? Like so, if we ask like can an AI model like actually learn on any level? To me, when you say that the models they don't learn, that there is 0 instances of learning, it's 0%, right? That means then that if there's like 1% learning involved, if there's an instance where a model is shown to learn something or some sort of behavior or shown some sort of function that will be classified as learning, then that means that it's more than 0%, even if it's the most awful thing on the planet at it. Right? And then so to me, that's this same exact concept with the Nubit. So with the Nubit, what we're doing is we're simulating as best as I can with very limited hardware, like a qubit, but 1/1,000,000th of a qubit, essentially, like the least powerful version of a qubit that I could possibly think of. And then so the reason why we simulate this and we create this is that so if there's quantum mechanics or things that we can learn from quantum mechanics and quantum functions, then whether or not we're looking at a qubit or a Nubit, we should be able to verify and measure something, right? At some sort of level of variation. And then so that's to me where the significance of the Nubit comes in, because it allows us to take those measurements, which is exactly what we're looking for within these tests. Does introducing quantum mechanics into the RPSO's form algorithm in this instance do something? Does it make these numbers go up in any way, shape, or form? And in any way, shape, or form that is beyond like statistical variance. And then what we can see in every single instance that we're looking at within this notebook here is that yes, we can see by introducing a Nubit in this instance, the least powerful unit of quantum mechanics that we can introduce into this notebook, we have some sort of impact on the mathematical models. And then so does quantum mechanics have an impact here? Yes. It has a measurable impact. What exactly is the impact? What exactly does that mean? What are the implications further than that? I can't tell you. I can tell you that it very clearly has a measurable mathematical impact, which is step one, and cool in my book, right? That's all I want to do within this is I don't have access to quantum computers. I don't have access to a Kelvin refrigerator, like all of the things that would be necessary to do that. But I still want to play around with quantum mechanics on some level. So I created the Nubit to allow myself to do that. And it works out pretty cool here, as you can see in this instance. I'll name this notebook and leave it in the description of this video. And if you like this type of content, please like and subscribe. Thank you very much.